Hi, my name is Patrick Struck, and this is the presentation for the paper Quantum Indistinguishability for Public Key Encryption Scheme, which is joint work with Tommaso Gagliardoni and Juliane Krämer. Let's start with the motivation and the background for this work. We look into public key encryption schemes where we have two parties, Alice and Bob. And when Alice wants to send some message M to Bob, she will use the public key of Bob and encrypts the message with it to get some ciphertext C. And she will send over the ciphertext C to Bob, and Bob will use the corresponding secret key in order to decrypt the ciphertext to get the message M. In between the communication, we have the adversary who can see the ciphertext C and tries to learn anything from C about the message. So the idea behind a secure encryption scheme is that the adversary should not learn anything about the message M from the ciphertext C. This is formalized in notions like qINDqCPA security for ciphertext indistinguishability. For the public key case, they essentially boil down to this indistinguishability phase, where we have an adversary and a challenger. And the adversary will send two messages, M0 and M1, to the challenger. The challenger will then flip a bit B at random. Depending on the bit, will encrypt either of the two messages and send back the corresponding ciphertext CB to the adversary. And then the adversary, or the goal of the adversary, is then to determine this bit B chosen by the challenger. Regarding the computing power of the adversary and the challenger, we can distinguish between three different cases. So the first is classical security, or also QS0 security. And in this case, both the adversary and the challenger are classical. Then we have post-quantum, or QS1 security, in which case the challenger remains classical while the adversary gets quantum computing power. And finally, quantum, or QS2 security, where now both the adversary and the challenger are quantum. Now, for the first two cases, classical and post-quantum security, the picture you can see here, this gives us the correct security notion, because the fact that the challenger is classical limits any communication between adversary and challenger to be classical. While in the QS2 setting, where the challenger now is also quantum as the adversary, then the two could communicate quantumly. And this is now also the focus of this work on this QS2 setting. Before we continue, let's do a quick recap on quantum operators. So here you can see the unitary, or the quantum operator for some function f. So it takes two input registers. So the first one corresponds to the input of the function, the second one corresponds to the output of the function. And so if we feed in x and y into the operator, the output will be x and then y XORed with f of x. This is what we call a type 1 operator, and these operators are essentially realizable for any function f, and we know that they are efficiently realizable if you can efficiently realize the function f on a classical computer. And they are, for instance, used in the quantum random oracle model. Now, when we look at a type 1 operator for an encryption scheme, they will look as follows. So for the input, we have then the register containing the message. And for the output register, consisting for the ciphertext, we have some value y. And then the output will be the message and then y XORed with the encryption of the message M. Now, in this picture here, we assume that the public key is fixed. So this is a parameter of the corresponding unitary. And also the randomness used for the encryption is implicit, so we don't explicitly state the randomness as input-output registers. Now, the first notion of indistinguishability, which goes beyond the post-quantum setting, was analyzed by Boneh and Zhandry in 2013. So, and they use these type 1 operators we've seen on the previous slide. So in this notion, the adversary will send three registers to the challenger, two message registers, here M0 and M1, and one ciphertext register Y. Then the challenger will flip a bit and then run the type 1 encryption operator on one of the two messages together with Y. And then he will send back all the registers, so M0 and M1, together with the register containing now Y XOR with the encryption of the message MB. to the adversary. The observation that Boneh and Zhandry made is that the ciphertext register, this will be entangled with one of the two message registers, namely the one with the message MB, while the other message register remains unentangled. And they show that the adversary can actually detect this entanglement, which makes this notion unachievable for any encryption scheme. Simple solution, what one can think of, is what happens if now the challenger would actually withhold the two message registers and only send back the ciphertext register to the adversary. But in this case, you can show that this makes the notion equivalent to the case of classical messages. So we would fall back to the post-quantum setting here. This means that up to this point, there is no security notion for public key encryption schemes with a quantum indistinguishability phase. But here I'd like to point out that in concurrent and independent work to ours, Chevalier et al. Also developed quantum security notions for public key encryption schemes, which also allow a quantum indistinguishability phase. Now, before we come to what we did in this work, let's again look into the operators. So here we have again the type 1 operator you've seen already, but there's also a different way of realizing these quantum operators. Namely the following: instead of having this input and output registers, we just have one register containing the input, here X, and then there's only one output register, which after applying the operator will contain the value f of x. Now this is what we call a type 2 operator, and they have first been analyzed by Kashevi et al. In 2002. And one important thing for this is these operators are only realizable for reversible functions. So for instance, you can never realize a hash function with such an operator because they're not reversible. And the other thing, these operators are very strong in the way that it's not always clear that you can actually efficiently realize such an operator. Based on these type 2 operators, we develop a new security notion in the QS2 setting. So our security notion called qINDqCPA works as follows. So again, we have the adversary and the challenger, and the adversary will send two message registers M0 and M1 to the challenger. The challenger will flip a bit B at random. Depending on the bit, we'll discard the message M1 minus B, and then it will apply the type 2 encryption operator to the other message MB. And what you can see here is we now explicitly de-randomize the operator, so you can see we have the randomness as both an input and an output of the circuit. And then for the second register, what happens is that the message MB will be transformed into the encryption of the message MB using this particular randomness. So, and this randomness, this was something that was implicit in the security notion you've seen before by Boneh and Zhandry, but actually it's required in order to ensure the reversibility of the operator. Now then, after computing or evaluating the type 2 operator, the challenger will send back the ciphertext register to the adversary. Now the difference here is that the adversary now does not get the entangled registers, as was the case for the Boneh-Zhandry notion. Thus we can avoid the impossibility result they propose. And the second part, now the randomness which will be chosen by the challenger is classical, which means this will not be entangled with the ciphertext register, and therefore it's fine that the challenger actually withholds the randomness register and not giving it to the adversary. But the same also applies to the Boneh-Zhandry notion. The main question now is, we use these type 2 operators, and as already mentioned, they are quite strong, and it's not clear that you can actually realize them efficiently. So the question is, can we actually do this for public key encryption schemes? And for this, we first show this for perfectly correct public key encryption schemes, so when there are no decryption failures. And the way we can build this operator works as follows. So we have the randomness register and the message register. Then we set up an auxiliary register containing a 0. And then we feed all these three registers into a type 1 encryption operator. This will give us as output the randomness, the message, and then for the output register now the ciphertext. Then we can flip the message and the ciphertext register and feed them into a type 1 operator, a type 1 decryption operator, which then means that the ciphertext, which was the input, will also be outputted by the type 1 decryption operator, while for the output register we would get the message XORed with the decryption of C, which will be the message again, so the output will be 0. And now this dashed box here gives us the type 2 encryption operator. And on the downside, what we can see here is that this type 2 encryption operator requires knowledge of the secret key. So you can only do this operator if you know the secret key, which is a potential issue. And the other question now is, what about schemes with decryption failures? Because in this case, you cannot run the type 1 decryption operator here because it will not always give you output you 0, which is a crucial thing here for this type 2 operator. And to solve this issue, we define what we call recoverable public key encryption schemes. And the main idea here is that the randomness or knowledge of the randomness allows you to perfectly decrypt ciphertext even without the secret key. A bit more precisely, so if there's some recover algorithm which takes as input a public key, the randomness, and then the encryption of an arbitrary message with this public key and the particular randomness, that this one outputs you the message with probability 1. That's what's a recoverable public key encryption scheme. And examples for this are essentially all the lattice-based and code-based PKE schemes we are aware of. Now for recoverable public key encryption schemes, we can also realize this type 2 operator in a slightly different way. So again, we start with the randomness register, the message register, and this auxiliary register with a 0. We again feed all these into a type 1 encryption operator, which will output us the randomness, the message, and now the ciphertext. And now we use the type 1 recover algorithm with the randomness, the ciphertext, and the message, which means it will output us the randomness and the ciphertext, and then XORs to the message the output of the recover algorithm, which will be the message. So this gives us the 0 for the output. And again, this dashed box here gives us the type 2 operator for recoverable PKE schemes. Now here we have that the type 2 encryption operator requires merely the public key, because both the encryption and the recover algorithm only require the public key. Finally, coming to the application of our new security notion, so we look into the qINDqCPA security for several reward PKE schemes. More concretely, we look into the code-based public key encryption scheme Rollo2, the canonical LWE-based public key encryption scheme, and the hybrid encryption scheme. And for all of these schemes, we show that they are recoverable, which means you can realize this type 1 encryption operator using merely the public key, using the construction we've seen 2 slides before. Now here's the encryption scheme Rollo. So you have the key generation algorithm and the encryption algorithm. But actually the only part that's relevant for now is the one ciphertext component C1, which is the part that actually contains the message. And this will be computed by taking the message and XORing something that you compute from the randomness to it. So essentially, the message is encrypted using a one-time pad, which means we can use the insecurity of the one-time pad against superposition attacks to break the scheme. And how the attack would work is the adversary prepares the 2 messages, and for the message M0, it will create an equal superposition over all the messages, while for the message M1, it will just pick a classical message at random. Now, in case the bit B is 0, then the equal superposition over all the messages will be encrypted. And in this case, it means every message will be encrypted with this O of E, which essentially means the output will still be an equal superposition, because the one-time pad only acts as a permutation of the amplitudes, which are all the same for all the messages. On the other hand, if the bit B is equal to 1, then this one randomly chosen classical message will be encrypted, so we just get a random classical ciphertext. And these two cases can be distinguished almost perfectly by measuring it in the Hadamard basis. So essentially, we can always, or the adversary can always detect this equal superposition in case the bit is 0, while it only has a negligible chance of misjudging the case b equal 1 to be the case of the equal superposition. Next, we come to the hybrid encryption scheme. So here we again have the key generation and the encryption algorithm. And then the scheme is constructed from a symmetric key encryption scheme and a public key encryption scheme. And it will take the symmetric key encryption scheme, picks a key at random, and then use this key to symmetrically encrypt the message M, which will give us the ciphertext C1. And then the used symmetric key will be encrypted using the underlying public key encryption scheme. And then decryption works in the obvious way. You first decrypt the C2 to get back the symmetric key K, and then you will use this key K to decrypt C1 using the underlying symmetric key encryption scheme. What we show for this scheme is if the underlying public key encryption scheme achieves post-quantum or QS1 security and the underlying symmetric key encryption scheme achieves quantum or QS2 security, then this hybrid encryption scheme achieves our qINDqCPA security notion. And the idea here is that the underlying public key encryption scheme is only used to encrypt the symmetric key derived from the randomness, so it will be a classical key. That's why for the underlying public key encryption scheme, we only need security against classical messages. While for the underlying symmetric encryption scheme, there we will actually encrypt the message, so this has to be secure against encrypting messages in superposition. Now what we have seen is for Rollo 2, as a standalone PKE scheme, it does not achieve the qINDqCPA security notion, while it does achieve this notion if it is used in conjunction with the quantum secure symmetric key encryption scheme. This means that security mainly depends on the use case. So for instance, for the NIST standardization process, actually the post-quantum security is sufficient because there the main goal is on key encapsulation mechanisms. So the public key encryption schemes are used to actually encrypt the symmetric key that you will then use for communication. But we've also seen that this can cause potential problems if you use a public key encryption scheme in a larger protocol where you might actually encrypt the actual message with the public key encryption scheme. Now to conclude, so we give a novel quantum security notion for public key encryption schemes, which is based on the type 2 operators. We show that you can efficiently realize these type 2 operators for schemes that are perfectly correct or recoverable. And we give both positive and negative results for existing public key encryption schemes with respect to our qINDqCPA security notion. This concludes my presentation. Thank you very much.